In this lecture of steel structures, I will discuss the basic design philosophy of steel structures design, steel structure, types of structural steels, and structural steel sections. First of all, basic design equation. In design, the applied forces and moments due to external loads are equated to the maximum resistive forces and moments by the member material. Means we equate the applied loading with the material strength. The concept may be summarized by the following design equation. Here, the load effects are multiplied with the factor of safety, and it is equated with the maximum internal resistance offered by material of structure. Means applied loading is equated to the internal resistance or the material strength, and we enhance the load by a factor of safety. Why? To accommodate many factors like material deficiency, poor workmanship, natural disasters. So all types of things we cover with the factor of safety. So this is the basic design equation. Factor of safety. Factor of safety is required to bring the structure from the state of collapse to a usable state. If we do not give the factor of safety, then there is a chance that our structure may go to near collapse position. So to avoid that, we provide the factor of safety so that our structure remains safe going towards the collapse, and the structure will be remain in the usable position. Why factor of safety use? Here are following factors. Factor of safety covers following aspects. First, uncertainties in applied forces or loads. In the design, we always assume the loading. For example, this much of loading, this much number of people will come onto the slab. All things we assume, but do not know the exact value of the load, like 20 kilonewton or 21.2 kilonewton. So that's why all these uncertainties are covered in the factor of safety. The deflection should be small at service load conditions. So when we have applied the factor of safety, means the design load, for example 20 kilonewton, the requirement of the client, please design my beam, my slab for 20 kilonewton, but we provide the factor of safety and design the beam against 25 kilonewton. So that's why there is a 5 kilonewton margin. We have designed our member. So these all deflections will be covered under the factor of safety. To cover uncertainties in material strength, for example, during the manufacturing of steel, there is chances that the material do not after the molding do not become the homogeneous material. There are some uncertainties, or you can say there is some rusting. So all these things are also covered with the factor of safety. To cover in part poor workmanship, for example, during the construction of the steel building, the steel beam connected to the steel column, there is a poor workmanship. The bolts are not connected well, or the welding is not properly done. So there is a poor workmanship. So these poor type of poor workmanships are also covered with the factor of safety to avoid the accidents. The fifth factor, to cover unexpected behavior in case the theory is not fully developed. For example, we have developed stress-strain relationships, and there are theoretical backgrounds for the designing of members. All members are designed based on some philosophy, and if still there is any issue with the theory that is used for the design, that deficiency will be covered with the factor of safety. The sixth, to cover natural disasters. For example, when you design the building, there is no heavy wind, no earthquake, but when you provide the factor of safety, then your structure can survive under these conditions like heavy wind. The seventh, the stress is produced during fabrication and erection. For example, during the construction of steel building or any steel structure, there is a heavy stresses like due to hammering, due to riveting. So all these stresses are also covered with the factor of safety. Nominal strength. Nominal strength is defined as the strength of a structure or component to resist the load effects determined by the using formula given in the specifications. In the AISC, American Institute of Steel Construction, there is formulas given to calculate the strength of materials like tension member, compression member, okay, different types of members. The strength formulas are given. So by using these formulas, we got the strength of the material, that is called the nominal strength. Type of designs. There are basically three types of designs. First one, that is load and resistance factor design. The short name is LRFD, load resistance factor design method, or its other name is strength design or limit state design. These all names are of the LRFD. The second design method is the allowable stress design. The third design philosophy is the plastic design. I will discuss one by one. First of all, LRFD. In the LRFD, the major part of factor of safety is applied on the load actions called the overload factor. The minor part of factor of safety is applied on the right side of the design equation called the resistance factor or the capacity reduction factor. Okay, you in the start you have seen the basic design equation. On the left side there is loads and on the right side there is a material. So in the load resistance factor design method, the major part of the factor of safety, basically in this load and resistance factor of design method, there are two factor of safety that are applied on the equation. First one that is applied on the load side, and the second one that is applied on the material side. And the factor of safety which is applied on the load side, that is overload factor, and the factor of safety that is applied on the material side, that is reduction factor. That is again the factor of safety. This reduction factor is always less than 1. The resistance factor is lesser than or equal to 1, and it is applied on the material strength. Load and resistance factor design. The design equation is checked for each strength and serviceability limit states one by one. The strength and serviceability limit states I will discuss. And the strength, that is a material strength. For example, the steel material has a yield strength 250 megapascal. So that is the material strength criteria, that this material can bear the strength of 250 megapascal. And the serviceability limit stress state criteria is the deflection criteria. That, for example, you have designed a steel beam, then that steel beam do not undergo large deflections. So avoid these deflections. You have to also check against the serviceability limit to control the deflection criteria. So these are two criteria. Limit state is defined as the limiting stage in the loading after which the structure cannot fulfill its intended function due to strength or serviceability consideration. If any limit state exceed, then the structure will go under failure. So we have to must check the structure against strength limit state and serviceability limit state. Analysis of structure for loads is performed considering the structure to be within the elastic range. In the LRFD, we analyze the structure within the elastic range. You already know the Hooke's graph, that is against the stress and strain. Then we design the structure in the load and resistance factor design within the elastic range. This is the more realistic design as compared with the old allowable stress design. Now all the new books are coming in the market with the LRFD, not the ASD, allowable strength design, or the allowable stress design. So now let me discuss this one. Nominal strength is defined as the strength of a structure or its component determined by using the formula given in the specifications. And any this is the right side of the equation, and this is the left side, load. Any particular load effect increased by the load factors, that is factor of safety, is called required strength. that is the applied loading side, that is the material side. So now let's see the equation. The nominal strength reduced by the resistance factor is called the design strength. Here, that is the Rn, that is on the material side. If we multiply with the factor of safety, that is become the design strength, and on the load side, that is become the required side due to the applied loading. So here is the design equation, basic equation. Design equation in case of LRFD becomes Ru, means the applied loading should be less than or equal to design strength. In the applied loading, you have seen that that is increased by the load factors, factor of safety, and on the material side, the material is reduced by the reduction factor. So that is the on both sides factor of safety is applied. So that is the load and resistance factor design methodology. Allowable stress design. In the allowable stress design, the factor of safety is applied only on the material side and the loads are remain as unfactored. So factor of safety is taken on the right side of the basic design equation. This is denoted by omega. Okay, the factor of safety. So in the allowable strength design, we apply the factor of safety only on the material side. For example, if we have a material strength 300 megapascal, we divide it by 2, then we get the material strength 150 megapascal. That we will use for the allowable strength design. Plastic design, that is a third design. It is somewhat similar to LRFD, but here the analysis for load is performed considering the collapse mechanism of the structure. Okay, that is the yield phenomena after the load. When the load start increases in the steel members, then after the yield point, this the members start yielding, and this the failure mechanism starts. But after the yielding, there is margin of strength is present from the yield point. The ultimate strength means the steel member can still take the load from this region. So to accommodate to get this benefit in the design, this design methodology is called plastic design. Means after the yield point there is permanent deformations, or the other name is the plastic deformation. So that's why in this range the design is called the plastic design. Full reserve strength. So you can say this is the reserve strength we use in the LRFD only within the elastic range, not go into the plastic range. But in the plastic design we also go in the this plastic range or the permanent deformation. Full reserve strength due to indeterminacy of the structure, an inner elastic portion of the structure is utilized. Means in the plastic design the full strength, in the elastic region plus plastic region the full strength is used. That is the methodology or the philosophy of the plastic design. In elastic material behavior is considered in the analysis and design. Inelastic behavior means after the elastic portion there is an inelastic region, so that is used in the design. Deflections and other serviceability conditions becomes more important along with the strength requirement, because after this there is lot of deformations to accommodate, to consider, or to control these deformations. So serviceability limit criteria will become more prominent, okay, or more important.